wasn't. Okay, welcome to yet another installment of the pre-calculus videos. This is section 6. This is called transformations of functions. Okay, our objectives: we want to identify a function as belonging to a family of functions. We'll talk about that, and then analyze a function rule or graph to determine transformations of the parent function. So when we talk about transformations of functions, this is when we, transformations is where we, we slide functions, okay, and we call that like a translation, not to be confused with languages being translated, okay, but and it's just physically just like moving a function in a certain direction, reflecting, okay, and that's kind of like a mirror. We could also talk about, kind of like even like, I wouldn't say we're going to do any rotations today, but like slides, reflections, dilations, and that's like a, stretching or compressing. So stretch/compress. Okay, so that's pretty much what we'll be doing, and so we have to look at what's called parent functions next to see that. But what we'll be able to do is we'll be able to take these like parabolas and rewrite them and regraph them, like flipping it down and like shifting it over. This is kind of the idea. So these are your standard parent functions, and so these are the most basic, easy functions. So these are just the basic types of functions. Okay, and so like the first one we have is f of x is equal to x. Okay, and I would even rewrite this and say like y equals x. Okay, and that's just your most basic line, and it's a slope of 1, y-intercept is 0. Okay, and that's just something that we need to know. Okay, the next one is a quadratic, and that's y equals x squared. Okay. And it's important we know that, and it's important we know a couple of those points, like the points 1, 1, and the points like 2, 4, negative 1, 1, and negative 2, 4. Okay, good points to know. Same thing with a cubic. Okay, it looks like this. Okay, and then we have an absolute value. Okay, we'll be manipulating all these. A couple of other parent functions, that we can talk about. Well, and let's do this. Let's do an exponential. All right, and I might be missing a few here, but an exponential would be something like y equals, say, 2 to the x. It looks something like that. Okay, just to know what they look like. Another one would be a logarithmic function. Logarithmic. Okay, and that would be like y equals log base 2 of x, and that would look something like this, okay? And we've talked about those, but we just need to know what these shapes look like. The next one we have is the square root, okay? And the square root would be like y equals the square root of x, okay? And that graph would look like this, okay? So we just need to know like the general shape of the graph, not necessarily, technical exact points. It always helps when we do. Some of them will need to know that, but not necessarily for every single one of them. So let's go ahead and take a look at this one. And it says, use the graphing calculator to graph each function and find the matching graph. So, and we kind of just did that already, okay? We found, we had a cube root function, okay, that wasn't part of our parent function, but an exponential function. We just went through that, okay. Which one? That would just be D. It'd be this one here, okay. And we just need to be able to look at a graph and just be like, okay, that's an exponential function. That's what it's going to look like, okay. So this would be D. The logarithmic one kind of looks like A or B, but the difference with with a logarithmic versus a square root, has a vertical asymptote, and it stops at that point 0, 0. So A is a logarithmic function. Okay, cube root function is actually going to be c, kind of by process of elimination, because b, we know this function to just be the function y equals the square root of x. Okay, so that's the idea. All right? All right, so then what we have is something called a translation. Okay, and this is a slide. Okay, I call a translation like a slide. Okay, it's like a shift. Okay, and so what we have is this. When you have this definition here, f of x minus h plus k, okay, h is a, so if it's inside the parentheses like this, h is a horizontal shift. And it's always, we always shift in the opposite direction of what the sign says. So opposite of what the sign says. So opposite of the sign. Okay. And then k, and horizontal, remember that's left or right. Okay, it's going to go in this direction, left or right. Left or right. Okay, but the k, this value, is a vertical shift. Okay, this means we're going to shift it up or down. Okay, and this, it stays with the sign. So this is the same as the sign. Okay. All right, so the example we have, all right, you know, and if we just kind of look at this, all right, you know, we have this parent function f of x is equal to the square root of x, okay? And what we have here is we have a different function, and the function is the square, or the, I'm sorry, absolute value of x, not square root of x. Take the absolute value of x minus 2 and then add 1 to it. And so what you notice here is that we've shifted the graph, okay, so since h was a negative 2, this means 2 units right, okay, and this plus 1 means 1 unit up. Okay, so, you know, just thinking about a graph like this, you're like, well, I don't really know what this graph looks like. But if you knew the parent function and you understand transformations, it really isn't that big of a deal. So what I'm going to do is that for every point, especially our corner here, 2 units to the right, 1 unit up, and then we plot another point. You know, and if I take...
There's no dilation.
No, there's no dilation, yeah. So if I take, and even if I start at this point 1, 1, and go 2 units to the right, and then 1 unit up, it's going to translate those same points. Okay, even if I did from this point, 2 units over, 1 unit up, okay, lands us that same point. Okay, so that's the idea. All right, so then it says, okay, and let's kind of, let me do something here. All right, so here's that video, just the animation, and so I want you to see, you know, here's our regular function, and that's that function in red, okay, here. And then we have the, so that's our parent function, and then what we have is this manipulated function here, where we can manipulate the value for k, and when I move that, it just moves it up and down, okay? But if I manipulate the input, then that's going to move it left and right. So if you manipulate the k value, it's a shift up and down. Manipulate the input value, it's a shift left and right. And that's the idea. So, and so, you know, you can plug in different values, you know, whatever. What happens, you know, we'll talk, you'll figure all that out later. Okay, the next thing that we have on the next page is reflections, okay? And so what we would say here is that if we make, so reflections happen, okay, when we change the sign of, so that's when we change the sign in front of a function. Okay. Now, if we make the entire function negative, so here, where that negative comes in, okay, that means that we made the entire function negative. Entire function negative. Then what happens is we reflect that about the x-axis. Okay, so if you had your original function here, okay, and that was just the square root of x, if we make the entire thing negative, then we reflect that over the x-axis, okay? If we make just the x value, the input, so just change the input, okay, not the entire function, change the input, which is like your x value, okay, then that reflects about the y-axis, okay, and you can see that here, that if I were to take the square root of x, okay, take that function, and then instead of making the entire thing negative, if I just make the inside portion negative, then it just flips it over the y-axis, okay? All right, same thing kind of down here, so we can kind of put all these things together, okay? Now what I've done here, all right, so you've got this original function, f of x is equal to x squared. There's our parent function, okay? Now if I have this negative 3, okay, that means that we shift it, so we shift 3 units right, okay, and then 2 units up, okay, and we did that in the last one. So you know, if you want to take this original point here, 0, 0, we shifted that over. Let me do this. Okay, that was 1, 2, 3 units over, and then 2 units up, and that gives us the vertex here. Okay, but what we had done was we would, you know, typically would have the graph opening up. But the problem is that we've out here, okay, we have made the entire function negative. So we've made the entire function negative. So that means that we need to reflect it over the x-axis. So we reflect over the x-axis. And so then what you have is you have this parabola that just opens down, okay? All right, the next thing we need to talk about is a dilation, okay, and that's a stretch or compression of a graph, either horizontally or vertically. And so it comes with this value of a. So if we take the function, and it comes from this multiplier of a, so this multiplier. And so what happens is if we have a number that's between 0 and 1, okay, between 0 and 1, so if this number is a fraction, say like a half, then we get a compression, okay? And then if the number is greater than 1, okay, then we get a stretch. And so here's what I like to think, okay? If the number, all right, hold on. All right, so let's just take a look at this function. So we have our normal function, our parent function here, the cube root of x, okay? But when we apply a multiplier out here, that's going to change the way the graph moves. And so if this number is smaller, okay, if its number is a fraction, then the graph gets, I guess, you know, it gets compressed, okay? It gets kind of like, you know, these values get smaller. And let's take a look. Let's do another one of those animation things, okay? Let's do one of those. All right, so if we take a look at this, you know, you have this parent function, ax squared, okay? If I change the value of a, if I make a smaller, then the graph gets fatter, okay? And if I make a little bit bigger, then the graph gets skinny, okay? And so I had like a way of remembering it, and it was like, if you're fat, then you need to eat less. Okay? And then if you're skinny, then you need to eat more. And so that kind of helped me remember what that value for A was. So if you're fat, you need to eat less.
That makes sense.
If you're skinny, you need to eat more. Okay, that's kind of how I remembered it. So so that's what that is, okay? And that's just a, you know, a dilation. Okay, you can have a horizontal stretch too, okay? And that's if the value for A is inside of your input, okay? And again, it's kind of the opposite. So if you get a stretch, if A is less than, or if A is between 0 and 1, and you get a compression if A is greater than 1. So let's kind of do something similar. Let's do another animation here so we can kind of see what's going on. All right, so on this, if you look at it, your value for A is inside the parentheses, okay? And then if you change the value of A, if you make it smaller than 1, then the graph ends up getting fatter, okay? But you get a horizontal stretch.
Yes.
That's the difference, okay? But if you make A bigger, then it becomes skinny. So it has the same effect. It's just depending on how you want to talk about whether it's going to be a vertical stretch or a vertical stretch or horizontal stretch dilation.
Yeah.
Okay, so that's that. Okay, on this last one, what it's wanting us to do is it wants us to use our knowledge of transformations to find the matching graph. So, and the thing we have to understand here is that, when we look at all these different functions, what we notice is that all these functions have a square root. So the first thing we need to do is recognize our parent function. Okay? So the parent function is the function y is equal to the square root of x. Okay? And so remember that graph just looks like this. All right? We just need to kind of have a knowledge base of that. So the first thing that we're going to do is, I'm kind of, let's do this. I'm going to look at this one here. F of x is equal to the negative square root of x plus 2. Now this x plus 2 means that I'm taking this point here and shifting it over 2 units, okay, which does this part here on A, and then the negative makes it go reflected over the x-axis. So this is graph A, okay? Now if I do 2 times the function x plus 1, okay, if we do x plus 1, that's going to be, we're going to move it to the left 1 unit. Okay, and the only graph that's done that is part D, and then we multiply it by 2, so it got bigger.
Yep.
Okay, so this is D. Okay. The next one is 1/2 square root of x minus 1. So what we did is we took this minus 1 as a shift down 1 unit.
Yeah, because that's not under the...
So if we start here on this point here, then, we move down 1 unit, and that's what happened here, okay? And then we have a 1/2, so it got kind of skinny.
Yeah.
So this is graph B. By the process of elimination, this is graph C. But what you can see is that it's been negative, so it's reflected over the x-axis, and then it's multiplied by a factor of 2, so it got a little skinnier, okay? And that's it. So hopefully it makes sense. Hopefully it's not too bad, but I'll let you go from there, and
Awesome.
that's it.